All right, guys, here we go. Here's a little review for our upcoming quiz. So first off, we have the chain rule for integration, sometimes also known as the fundamental theorem of calculus. So if you remember how to do these, we're giving some function. We're given f of x is a function of x, which means we have x's in our bounds. In this case, we only have one x in our bound. We're going to have some integral problem with some other variable in it. In this case, we have t's. We want to calculate f prime and plug in a number, in this case, a equals pi. So how do we do that? Well, actually, it's quite easy. If I wanted to write down f prime of x, we'll start there. What I do is I take my function in my integral, and I'm going to kind of write it down with parentheses. Now, you don't have to do it with the parentheses. I think it's just easy to see on a first example. All right, so instead of t's, I have parentheses. And what do I plug in? I actually just plug in my function. So this is sine of x, sine of x. And then I multiply by the derivative of the thing that's floating around in the bound of the integral. So the derivative of sine x is cosine of x. So there's f prime of x for this problem. And that's how it always works. We take our function, we plug in our functional bound, right? Sine of x in this case. If there's two of them, we'll see how that works in a second. And we don't plug in our constant, right? We worked with this before. That if we plug it in, that gives us a constant, and when we differentiate it gives us 0. So it's fine. But this is kind of our f prime of x. Now I need to plug in pi. So this will be f prime of pi is going to be sine of pi squared plus 5 sine of pi plus 6 times cosine of pi. Sine of pi is 0. Yeah, sine of pi is 0? Yeah, sine of pi is 0. So this will be 0 plus 0 plus 6 times cosine. Cosine of pi is -1. Times -1 equals -6 is your final answer. All right, so we take our function in our integral, we plug the function in our bound in, then we plug in our number afterwards. So we'll do one more. Now, this one, number 2, I guess. We haven't really done a problem like this before, but it uses kind of the same techniques of what we've done in other problems. So I'll show you how to do it. What we know how to do is, like we did above, there is exactly one function in my bound and one constant. Here we have two functions in my bound. But we could fix that. We could figure out how to deal with that kind of in a simple way. What I can do, if you remember, I can split my integral up into pieces, right? And as long as those two pieces, the bounds match in the right way, they add back together to the original guy. And now the only thing we do have to be careful about, though, is we need a number that we can actually plug into each of these. Right? We don't want anything undefined. We don't want anything weird happening. Excuse me. Like maybe 1 is a good choice. I can plug 1 into e of x. I can plug 1 into ln of x. So what do we have? We have, this will be the integral from e to the x to 1 of 3t squared minus 4 over 2t minus 1 dt, plus the integral from 1 to ln of x, and then the same thing. Right, so I can split that up into those two integrals. Now this one on the right follows the same rules we've seen before, but this one on the left we can't quite do yet because our function is on the bottom, but to fix that, I can slap a negative sign in front of it and swap my bounds. 1 to e to the x, and I'll just copy and paste this whole thing. Okay, and now we can just do our trick from before for this first guy. We can just do negative. Now, if you remember, we ignore the constant, plug the function into for the t. So I get 3 e to the x squared minus 4 over 2 e to the x minus 1. And then I multiply by the derivative of the function. The derivative of e to the x is just e to the x. Now for this guy, oops, same thing. I take my function, I plug in ln, so I get, I guess, plus 3 ln of x squared minus 4 over 2 ln of x minus 1, and then times the derivative of ln, which is 1 over x. Right? And then for the problem, what do they want me to plug in? They want me to plug in 4. So this will be negative 3 e to the 4th squared, which is e to the 8th, minus 4 over 2e to the 4th minus 1 times e to the 4th plus 3 ln of 4 squared minus 4 over 2 ln of 4 minus 1 times 1 over 4. There's a good final answer. So that's how we do problems of that type. I'll leave the other two for you to do, and you can check your answers against the answer key. And let's pop down to L'Hopital. L'Hopital. All right? I'll do the first 4, you do the second 4. So for number 1, I plug in 0. I get sine 0 over 0. Sine of 0 is just 0. So this is 0 over 0. Okay, great. I can L'Hopital. So we have the limit as x goes to 0. And what do we do? Well, we take our derivatives, right, to L'Hopital. So I get cosine of x over 1. When I plug in 0, I get, I guess, cosine of 0 over 1. Cosine of 0 is just 1. So this is 1 over 1, which equals 1. So my limit is 1. All right, so that one's pretty easy. And you might actually recognize this function as one of our special limits from last year. And it's actually really easy to calculate with L'Hopital. All right, so let's do this guy. 1 minus x squared over e to the x. I plug in infinity. I get 1 minus infinity squared. So this is what? Negative infinity over e to the infinity is just infinity. So this is L'Hopitalable. So I'm just going to have the limit as x goes to infinity of, I take the derivative of the top, I get minus 2x. Take the derivative of the bottom, I get e to the x. And this is still negative infinity over infinity. So I L'Hopital it again, get the limit as x goes to infinity of minus 2 over e to the x. If I plug in infinity, I get negative 2 over infinity, which is 0. So the limit here is 0. So both of those fairly easy. Both of those fairly easy. All right, number 3. I plug in 7 to the top and I get 0. I plug in 7 to the bottom. Do I get 0? I don't think I get 0. I don't get 0 on the bottom. So that's good. I get, what's that, 56 minus 49 is 7. And then 7 minus 15 times 7. 15 times 7 is 105. So 7 minus 105 is something. 7 minus 105 is negative 98, which is just, this is just 0, right? So this isn't 0 over 0. It's not infinity over infinity. It just ends up being 0 over a number, which is 0, and that's fine. Okay? And then we try this last guy, number 4 here. Plug in 2. If I plug in 2, I get 1 to the 1 over 2 minus 2, which is 1 to the infinity, which he said is one of our indeterminate forms, but it's not one of the ones that we know how to deal with. And the trick to then doing this is logarithming everything in sight. So we're going to ln x squared minus 2x plus 1 to the 1 over x minus 2, which is going to be equal to ln x squared minus 2x plus 1 over x minus 2. If I do the simplification, we've done a couple times already. So this is equal to that just by taking this exponent out of the logarithm. Now, if I were to plug in 2, I get ln of 1 over 0, which is, again, 0 over 0. So now I can L'Hopital. 0 over 0, I can L'Hopital. I take the derivative of the top and bottom separately. The derivative of the top is going to be 1 over x squared minus 2x plus 1 times 2x minus 2. And the derivative of the bottom is just 1. So this is 2x minus 2 over x squared minus 2x plus 1. If I take the limit, so I get the limit as x goes to 2. On top I get 2, and on bottom I get 1. So the answer here is 2. My limit's not 2. My answer to this problem with the logarithm in it is 2. So now to undo the logarithm, I have to e it. So my final answer for this guy is equal to e to the 2, or e squared. All right, now try the other ones.